Is everyone cool? That all makes sense? I wanted to give you another puzzle. Here's the last puzzle, and then we'll move on to the next technique. This is a famous guy, Huffman. And you might have heard of Huffman encoding. And the fun story is Shannon, who I've talked about a lot, Claude Shannon, the information theory guy, is very interested in information theory. And part of information theory is how many bits does it take to represent a piece of information? That's sort of a measure of the content of that information. And you can see that the number of bits it takes to represent a piece of information isn't a really obvious thing. Like if I wanted to store, I'm going to write something on the board, work out how many words it takes to describe what I'm writing on the board. For this one, you probably can't get better than 3. If you say 621, suppose that's a 3-word, suppose they're all separate words. 621, yeah. You probably can't do better than that. But what if I said, you know, there's probably some enormous number and I could say the 10th Mersenne prime. So I don't actually have to say the number, I can describe it in less.
Just a million.
Yeah, a million. Yeah. A million, 2 words. 1 million. What about, you're describing a series of, what we used to do when we'd proofread things in the old days, before computers were widespread. Someone would type a document up and then you'd make a change to it, and then he'd give it to the secretary, she'd retype the whole document with the changes. But of course you could introduce, or he could introduce errors in the typing process. So how do you check that the 2 documents are the same except for this tiny little typo change you've made? You could hold it up to the light and all sorts of things. But the way we used to do it was we'd read, there'd be 2 of us doing it, one reading and the other one checking the other document. But if you read the words out and typos, because your brain gets confused because there's lots of redundancy in English language, so we used to read everything backwards. So you just letter by letter read it backwards, or word by word read the document backwards. Does that make sense? So what if you saw this? You could say the, but you'd probably just say 5 the's. So you can see the amount of information content in something is quite hard to work out, and something like this, where the amount of letters takes up heaps more space than the information content, that tells us that this would be a likely candidate for compression. So the idea of compression is that's how you can compress files, because there's all this sort of redundancy here. You can just compress them to take the number of bits they really need. And so Shannon, who was really interested in information theory and compression and how to measure information and things and so on and so on, was naturally interested in compression. And he and one of his friends, who was at MIT, spent a long time trying to work out the best way of compressing things and an optimal way of compressing things under certain conditions. And they came up with a way, but it wasn't quite right. And this is one of my favourite stories. I love stories like this. And they asked, this friend of his had some students and they had to do an exam. And he said to them, oh look, either do an exam or solve this problem. And one of the students said, oh okay, I'll do the exam. No, hang on, I've got an idea. No, I'll solve the problem. And he wrote a little paper solving the problem. And he solved this problem that 2 famous professors could never even solve. It was just like, you know, his little end-of-year exam sort of thing. And, you know, it's very funny. And his name was Huffman. This is Huffman encoding. And how it works is something like Morse code. You know Morse code, they say, it's not like in ASCII, we say 7 bits or 8 bits for every letter. So you want to say a letter, you say 8 bits. So if I give you a series of letters, you know how many bits and space it's going to take up. But Morse code doesn't work like that, does it? Does anyone know Morse code? How would you say the in Morse code? Come on, you got to know Morse code. The entire exam's in Morse code. Does anyone know what T is in Morse code? It's dash. Thank you. And what's H? It's not 3 dots. It's 4 dots? No, it can't be 4 dots. It cannot be 4 dots. Oh, okay, then it's, Well, then Morse code, I was wrong. I thought it was a code that had 2 symbols, dot and dash. But it must have 3 symbols, which is dot, dash, and space. Yeah. Because I was thinking it couldn't possibly be 4 dots because I happen to know that 3 dots means SOS, dot, 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 dash, dash, dash. Yeah, it's S. So looking at that, you wouldn't know how to parse it. If I saw that, followed by that, does that mean S, whatever that means, or does it mean T, HT? Yeah. Anyway. So all right, it's a ternary system. So it's dot, 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 and THE. What's E? Dot. So the whole thing is only 1, 2, 3, 4, 5, 6. Only takes, I'm counting the spaces, yeah. The idea being in Morse code, to save time, letters that occur more frequently are given shorter encodings, and letters that occur less frequently are given longer encodings. And then on average in a message, if you know the letter frequencies in advance, when you work this out, and the message actually follows these letter frequencies, you get a really nice short message. Does that make sense? And what they wanted to do was a way of doing this in binary. So we don't have our little spaces here. And so I want to encode E to be something really small, and I want H to be probably a bit longer, and Z might as well be really long, because my message is going to have lots of E's, so it's going to be a shorter message. So how can you come up with codes that you could assign to letters, so if you know the frequency of all the letters, so your overall message length is as short as possible. And the constraint being, you can't say that this is one letter and that this is another letter, because we don't have spaces in our thing, so we can't disambiguate that. It's got to be completely unambiguous. So once you've said that some letter is dot, 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 no other letter can start with dot, dot, dot. Yep. So how could you work that out? Oh, sorry, once you say a letter is 0, 0, 0, no other letter can be 0, 0, 0, 1. They're not legal encodings. You got that, or you got that. And if you didn't have this, then you'd also be allowed to have this. Yep. And the problem of how to actually work out for letters with a given frequency what bits patterns to use is a tricky problem, and Huffman worked out a really beautiful way of solving it. And it's very, very nice. So I thought I'd give that to you as a puzzle. You could just look it up, but don't. Instead, try and work out a little table for any message you want. Pick any bit of text and count the letter frequencies of the words, or just use the normal English letter frequencies and apply it to any old text. Come up with a thing that says, I'm going to represent an A as a 00101, and I'm going to represent a B as a 001001, and a C as a 1001, and come up with a table for all the letters in the alphabet and see if you can come up with the optimal one. Did you understand the puzzle? It's not worth any marks at all. It's just a fun thing. Yeah. Okay, so that's your puzzle. Now, we're now going to talk about the second strategy, possible strategy, for coming up with an algorithm for a problem. Like for the greedy method, this only works to particular problems, for particular problems. The problems have to have certain characteristics for this method to be used. This method is divide and conquer. Divide and conquer is again using our general sort of strategy of taking a big problem, and we're not able to solve it, so we reduce it, turn it into smaller problems and solve those smaller problems. With greedy, the small problems can all be independent of each other, like one is what will I have as dessert, and one is what will I have as my drink, and so on. With divide and conquer, it works in a different way. Divide and conquer is you work out, to solve a particular problem of a particular size, how to solve it by solving the same problem for smaller sizes. Does that make sense? So if I wanted to find the biggest person in the whole room, if that problem's too big, then a divide and conquer approach would be to find the biggest person in this half of the room, and then the biggest person in this half of the room, and then combine those answers in some way. Yep, that's divide and conquer. Yep.
There's also the multiply and surrender approach, where you make the problem larger and larger and larger and then give up.
It's the opposite of divide and conquer. I like that. That's fantastic. Did everyone hear that? Liam suggesting there's a multiply and surrender approach, where you just make the problem bigger and bigger and then it becomes hopeless and you give up. That's very, very nice. I like that. Okay. Oh, by the way, a design problem that someone said, I've just been flipping through some of the design diaries, I'm really enjoying them. One of the ones that's really good, and this was a Tute presentation, is someone said a bad design is whiteboard markers, because they look exactly identical to permanent markers, except for a tiny little word on there somewhere that says whiteboard. And that's really daft. So that's very, very good. And I had another example too, but don't worry, I'll move Now, when you can solve a problem in terms of itself, if you can keep applying this thing over and over again, because once I realised to find the biggest of the whole room, I can just divide the room in half and find the biggest of the two halves and then compare those answers. Once I've realised I can do that, then of course I can do it again to this half. Because the nice nature of this reducing it to the same problem is I now have a technique I can use to reduce that problem to even smaller problems. So you can recursively apply it over and over again. So the actual programs that implement divide and conquer solutions tend to be recursive programs. Yeah, they use recursive algorithms. Now divide and conquer is really nice for exactly the same reason that greedy method's really nice. Let's have a look at why it works. Oh, and in exactly the same sort of spirit as greedy, the reason we're looking at divide and conquer early on is when it works, it's fantastic, but it's not that common that you can use it in a real world problem. Suppose, suppose you wanted to sort a whole lot of numbers. Suppose you had n numbers. And the amount of work it takes to sort the n numbers, we're going to say is proportional to the amount of time. Remember, that's our measure of work, is how many instructions you execute, which is how long it takes. So it's the time to sort n numbers, which we'll just write as t. The time to sort n numbers, that's just a function, so maybe it's n squared plus 7 or something like that, depending on your algorithm. The time to sort n numbers, suppose it turns out that it's n squared. You've worked out some algorithm and you can sort numbers in n squared time. So if I give you 100 things, it takes you 100 squared seconds to sort them, or units of time to sort them. Now divide and conquer is really nice. Here's sort of how it works. Divide and conquer notices that in cases where, like this, where the complexity is greater than linear, so like where it's n squared, dividing the problem in half gives you an enormous bang for your buck. If it's a linear problem, like finding the biggest, well, dividing the problem in half doesn't really help you at all, because it just halves the amount of work you've got to do, and then when you do the other half, you've done the total amount of work you would have done before. Okay, so it's not really saving you anything. But with an n squared problem, what happens when you divide it in half? How much work do you have to do? You have to do a quarter's work, yeah. If instead of spending n seconds, you only had to, instead of sorting n numbers, you only had to sort n on 2 numbers, what's t n on 2? Well, you just substitute n on 2 into this. This is the definition of the function. So what does that give us? N squared on 4. Oh, I'll write it step by step. N on 2 squared equals, yeah, I'm just substituting, instead of n, I'm putting n on 2n. It's a bit confusing to do that, isn't it? No. No, it's all cool? Everyone's cool? Okay. That's n squared on 4. So I can solve half the problem in a quarter of the time. And how long will it take me to solve the other half of the problem? That will also take me a quarter of the time. So the total amount of time I've spent solving so far is n squared on 2. Now I need to combine them in some way. But you can see I've halved the total amount of work because it was an n squared problem. Breaking in half is just enormously good. So as long as the amount of work to combine those isn't vast, in this case as long as it's not n squared on 2, if it's linear, for example, which it will turn out to be, then that's fantastic. That means the total amount of time I'm going to spend is n squared on 4 plus n squared on 4 plus combining cost, which is n. That's n squared on 2 plus n. Which would you prefer to have, n squared on 2 plus n or n squared? Which is the best solution? Yeah, absolutely, except for trivial. Good man, you can have it. Do you have a jigsaw? Except for trivial values of n, you know, this is considerably smaller. If n's a million, this is massively smaller. What's a million squared? It's like 10 million, isn't it? So half of that, it's 5 million. You save 5 million. Oh, plus you have to add a million on. You save 4 million. Okay, so it's a massive difference. And furthermore, what did I do here? I took the original problem and I broke it in half. But what's the thing we can do with divide and conquer? Yeah, I don't have to stick with that. I can say, well, I'm not going to solve each of those halves using my crappy n squared algorithm. I'm going to break them in half. And I'm going to break them in half. And I'm going to break them in half. Does that make sense? So can you think of a sorting algorithm that uses this technique? Merge sort. Yeah, merge sort does this. Merge sort takes all the numbers, Splits them in half, sorts one half, sorts the other half. Yeah. Now, did we ever compute the complexity of merge sort? My recollection from 1927 is we guessed what the complexity would be and we substituted it in and we saw that it worked. But I never show you actually how to compute the complexity of merge sort. So I propose right now I will show you how to compute the complexity of merge sort. No? You don't want to do it? Why is that? Enough. I promise I'll only do it for 5 minutes and then I'll move on. Because I really want you to see it because it's a really neat trick. And in 2 weeks I've got a puzzle I want to give you. And if you see and remember this technique here, you'll be able to solve this other puzzle really nicely. Okay, so I have a vested interest in telling it to you. Here's how it goes. To merge sort two numbers, do you remember what you do? You've got n numbers. The trick is you break it into two half lots. You sort them and then you combine them. And you combine them, it's sort of easy to combine them then because these are sorted and these are sorted. So I don't know, if we're putting biggest on the top, say, and smallest on the bottom, you just compare the bottom two and whichever is smallest goes on the bottom of the new pile. Take it off this pile, whichever pile it is. Then compare the bottom two and compare the bottom two and compare the bottom two. And keep doing that until you've built up this whole pile here. You've put all the n of them into a single pile. And that will obviously take n steps to move, compare and move across. That's order n work, and you'll get all the n sorted. So you have to sort n on 2, you have to sort n on 2, and you have to merge. Now, with merge sort, let's say the time taken to sort is going to be Tn. We don't know what it is though. What is Tn? Is Tn n squared? Well, you do know what it is. What is it? You probably remember the complexity of merge sort. But no, it's good if you don't remember it. Let's suppose you've forgotten it. Okay. We can't remember what merge sort is. Let's just call it Tn. It's some formula. So whatever that formula is, this one here is going to take Tn on 2. And this one here is going to take Tn on 2. And this last step is going to take n. So we know that Tn is exactly the same as doing Tn on 2 plus, oh, those pluses look like t's, don't they? I'm going to make capital T's. Plus Tn on 2 plus n. So this is what we know, just by looking at what we do. The amount of time it takes to sort it is equal to the amount of time it takes to sort half, plus the amount of time it takes to sort the other half, plus the amount of time it takes to put together. We know that as sort of the definition. It's nothing interesting. From that equation, can we solve that and find out what Tn is? Well, I don't know. What if I said to you, x equals 3x plus 8? Could you solve that? How do you solve that? Oh, this is a clever thinking going on here. Move the 3x across the other side. That gives you what? Minus 2x equals 8. So x equals 4. Woohoo! You can solve it. Oh! Yeah. Yeah. I was going to try and pretend my equals had a minus hidden in it, but I couldn't pull it off. Yeah, except for that small little thing. Error. We got it exactly. So I wanted to show you that an equation where a term appears on one side and where a sort of related term appears on the other side isn't scary, though it probably freaked you out when you first saw it in primary school. And it's the same as this side. Well, you've got a function here and a function here, and it's the same sort of function that's on both sides. Don't freak out. It's just like a normal. It's just like normal. It's nothing wrong. It's called a recurrence because this term here recurs on this side. Yeah, this is defined in terms of itself. Here, x is defined in terms of itself, but it wasn't that scary, was it? Okay, it's exactly the same. So we know that Tn equals Tn. So I'm just going to now just do some very boring rewriting. I'm not going to use my brain at all because, as you can see from here, I have no brain left, and yet we'll be able to do it without even thinking. If I've got Tn on 2 and Tn on 2 and I add them together, what do I have? I have 2 lots of Tn on 2, and I've still got the n. Woohoo! So that wasn't hard. Now, I'm stuck, or am I? No, I'm not, because I think I don't know what Tn on 2 is. So I don't know how to go any further. But then I think, no, I do know what Tn on 2 is. Because what's T of anything? Yeah, T of n is defined as this. So T of 6 is 2 times T of 6 divided by 2 plus 6. So what's T of n on 2? Well, I'll just use the definition I've got on this side. Does that make sense? Quickly get it out. It's gone. It'll come, I'm sure it'll come. Tn equals 2. Yep, we're just about to work out what this thing is. We're going to zoom in on this. What is that term? What is Tn on 2? Will you tell me from that equation there, what's Tn on 2? What happened? It's 2 Tn on 4 plus n on 2. Now if that looks like magic, let's just see what I did. It's actually not magic. All I did was I just, wherever I saw n here, I replace it with n on 2. Yep. And I substituted n on 2 in, so whenever I saw, I put an n on 2. So everywhere there's a circle here, one last n. Everywhere there's an n here, I actually don't want to know for n, I want to know for n on 2. So instead of sticking an n in, I stick an n on 2 in there. Yeah? So that's going to tell me that T of n on 2 is equal to n on 2 on 2, which is n on 4, plus n on 2 on 2, which is n on 4, plus n on 2, which is 2 Tn on 4 plus n on 2 plus n. Whew. Does that look confusing? That's the only hard step in the whole thing. Do you see what I've done? I've just substituted it in literally. Wherever there was an n before, I'll put an n on 2 in. That's all I did.
Is it? The n on 4 is within the parentheses after.
Have I made a mistake?
Yeah, that's fine.
Oh, this 2 is... What's that? No, ask these questions. Some people are confused, so ask.
Okay, so you have what my answer? Well, anyway, so you have t, so, and it looks like it's t to the n on 4 in your box.
Here?
Yeah, it looks like it's t to the n on 4, but really it's t to the
n on 4.
space n on 4.
Oh, yeah. Oh. Let me think. Is that right? Yes. Yes, it certainly is. Now, that was an important thing. Thank you. Thank you. Is that even clearer than it was before? You see, before it seemed so clear. Now it's just clearer than clear. So that's n on 2 on 2. Yeah? N. Wherever there was an n before, I stuck n on 2. Is everyone happy? Wave at me if you're not happy. Just write that down. If you write nothing else in this lecture, write down these 3 lines, because that's the magic. Because now it's just really mindless what happens now. Now you just say, oh, that's equal to 2 lots of all this. That's 4 lots of t n on 4 plus n equals 4 lots of t n on 4 plus 2n. So I substituted itself into itself once, and I get this crazy expression. So now I've got 2 different expressions for Tn. The first one, and then the one when I expand at one level. And can you see I can expand it another level? I could just stick it in again. I could say, okay, what's Tn on 4? I don't know. I'll substitute it into this equation up the top. And I would find that it's equal to 8 times Tn on 8 plus 3n. And I could substitute it in again. Equals 16 Tn on 16 plus 4n. Whew. I can keep doing this forever. But I can't keep doing it forever. How far can I keep doing it for? It's like recursion. Does recursion go forever? When does recursion stop? The ground case. What's the ground case for sorting in a merge sort? When you're sorting 1. When you're sorting 1, how much work does it cost to sort 1? Nothing. Do you reckon? 1? Costs 1 bit of work to sort 1 thing? Okay. So I'm going to keep going until I'm just sorting 1 thing. So I'm going to say, in general, that's equal to 2 to the k t n on 2 to the k. Yeah, just double it k times. Here I've doubled it 4 times. Plus k lots of n. That's just a general form. I'm just going to keep substituting it, and I'll get the, if I stuck in k of 1, I'll get my first line. If I stick in k of 2, I'll get the second line. So you can just see we're just doubling each time, k times. I'm going to keep doing this, substituting it over and over again until I'm calculating t of 1, because I know what t of 1 is. What's that? T of 1 is 1. When is this going to be T of 1? When is this going to be 1 in here? When n equals 2 to the k. If n equals 2 to the k, what's k equal? K equals log of 2. Log to the base 2. Sorry. Log to the base, take log to the base 2 of both sides, and I get k equals log to the base 2 of n. Yes, that's right. If I take log to the base 2. So that's what k is, log of n. So if I do it that many times, if I say, oh, well, let's let k equal log to the base 2 of n, then I'm going to get 2 to the k, which is equal to 2 to the k is equal to n, times t of 2 to the k over 2 to the k, which is t of 1, and t of 1 is 1, so it's just n, plus k, what's k? Log n times n. So the amount of work that merge sort will do will be n plus n log n. Whew. Does that make sense? I hope so. Can I summarize the whole method we just did? We wrote down the recurrence equation just by noticing what it did. Then we just unrolled it a few times till we worked out what it was doing in general. And then we decided we'd keep doing it till we hit the terminal case, and we wondered what the formula would look like then, and that's what it equals. It's a very nice technique, and we'll need to use it in a couple of weeks to solve the problem. So fool around with it a bit. Do make sure it makes sense. If it doesn't make sense, please ask your tutor. Now, how long have we got? Oh, we've got like only 1 second, so I think we'll stop. I'll see you on Thursday, guys.